1.2 amps, back to the 1.2 amps, right? Then you have here a little coil. So let's say the radius of that coil is the radius of that coil is, let's say, 1 centimeter. Okay, and then you have n turns, let's say 10 turns. Okay, now let's say I drop this. So let's say the elevation from here to here is 5 meters. Then I drop this. So tell me at any instant in time, what's the EMF induced in the coil and what's the current in that coil as it's dropping. As it's dropping, it's moving faster and faster, 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 right, due to gravity. Wow, this is completely different than any of the other ones, right? All of these are all Faraday's law. Okay, so this guy is creating a B field, right? So what's the direction of the B field created by this wire? So then if the current is going this way, you curl your fingers around. So anywhere here, the B field created by that is into the board, right? Everywhere, it's into the board. But as this thing is dropping, it's going farther away from that wire. So it's going into regions of weaker B field, right, as it's dropping. It's going more and more into regions of weaker B field. So what kind of current should be produced here to try to help that B field? That's the way to answer, you see. What kind of current should be produced to help that B? So if the field is into the board, but you're going into regions of weaker B, you should try to create a counterclockwise, right? Yeah, you should try to create a counterclockwise current here so that the current will create a B field. No, hold on. What am I saying? You should create a, no, you should try to create a clockwise current so that the current will create a field into the board, because you've got to try to help this field. You see? Yeah. So it's got to be clockwise. So the current in coil is clockwise. Okay. So now let's actually do the EMF. Negative N. The area here is not increasing, the area of the coil. So we just have negative N A D B dt, right? So now how about the B? What's the B field created by this? I'm imagining this as a long current carrying wire, right? So what's that B field? Negative N area is equal to pi little r squared. And then the B field is going to be what? Remember, what was the current of what was the B field of a long current carrying wire? Mu 0 I over 2 pi r, where this r is this distance here, right? This from here. So it's not the same as this r. This r is the little radius of this guy. Maybe we can call this 2 pi d, right? So 2 pi d. I don't really like d, but let's see, what other variable can we see?
Oh, Professor, you can maybe do y.
Yeah, I guess we could do y, because usually we think of y from the ground up. But okay, that's fine. Let's just do y. Okay, so then you're going to have this pi will cancel that pi. Okay, so now what's changing here? The I is not changing, but the Y is changing, right? As you go this way. And the other thing we could do just to keep this track of the signs, we could say B field, since B field is into the board, it's actually negative, right? And then the two negatives will cancel and be positive. So then I have EMF is NR squared over 2 mu 0 I d by dt 1 over y. Okay, and then 1 over y, that's the distance that as it drops, it's increasing, right? So then I can say, okay, the EMF is NR squared mu 0 I over 2. So this is going to be negative 1 over y squared times dy dt. Right, so now I think this is where kinematics comes in. You say, okay, if V initial is 0, then y is going to be what? 1/2 times 9.8 times t squared. Right, it's just going to drop with the acceleration of gravity, 4.9 t squared. So then dy dt is going to be 9.8 t, the derivative of that. But let's see, dy is increasing. Yeah, okay, so then if I put that there, let's see what we get. EMF is NR squared mu 0 I over 2. Then there's a minus, and then the y is going to be 4.9 t squared squared, 4.9 t squared, and then dy dt is 9.8 t. Okay, so I have a general equation then that tells me what the EMF is at any instant in time. Negative NR squared 2 will go into 9.8, 4.9, and then one of the 4.9s will cancel. So then I'll just have negative R squared mu 0 I over 4.9. Okay, and then t will cancel the t to the fourth, and you will get t cubed. So I'll write it here. Negative n r squared mu 0 I over 4.9 t cubed. So does the negative match our answer just from analyzing the right-hand rule? We said that it's going to be clockwise, the current induced. Yeah, we said it's clockwise, and negative means usually clockwise. Yep. Right. So if you do the signs right, then this sign matches what you know from the right-hand rule. Some people prefer just doing the mathematical way, keeping track of the signs and then doing it that way. But I also like this. Whenever possible, I prefer this method if I can keep track of the direction by the right-hand rule, because I might have made a mathematical mistake here. So I don't want to rely on that always. But if the two match, then it's even better. Okay, so now we could say, let's calculate the EMF at t equals to 1 second. Okay, and then let's calculate the final EMF when it hits the ground. So you could either do it two ways, right? You can find the EMF at a particular time or the final EMF when it hits the ground. So then you're going to say, I think there's, how many turns were there? 10 turns. So this is 10. The radius was 1 centimeter. mu 0 is small, 4 pi times 10 to the minus 7. The current is 1.2 amps over 4.91 cubed. Okay, it's not going to be that big. Times 4 times pi times 1.2 divided by 4.9. So it's negative 0.00307 times 10 to the minus 7 volts. If I go negative, let's see here, go twice, and that'll be 10 to the minus 9. So negative 0.307 nanovolts. Very small voltage. Yeah, because the B field created by a current carrying wire is going to be very weak, right? So that effect is not as noticeable. Negative 0.307 nanovolts. Okay, how about the final EMF when it's hits the ground? When it hits the ground right here. So then we have to find the time that it takes to hit the ground, right? So then you have here, if the height is 5 meters, then you just say 5 is equal to 4.9 t squared. Oh, okay, it's almost 1 second anyway. 5 over 4.9 t squared square root. So oh yeah, it's almost like identical to 1.01 second. So it's almost 1. So of course, all that changes is that we put 1.01 here instead of 1. So what's happening as the time is getting larger, right? Then the EMF induced is smaller. Does that make sense? Let's see here why. So in other words, as it's dropping, you're creating less and less current in the wire. Why is that? Conceptually, try to explain that. So the reason that we got the t cubed on the bottom means that as time progresses, you're going further away from the wire, and the EMF induced in the wire is going to be less and less. And therefore, the current induced is going to be less and less. Why is that? See, mathematically here, what happened? You get d by dt 1 over y, and then the rate of change of d by dt 1 over y, you get negative 1 over y squared dy dt. So what's happening as the more you fall down? Dy dt, the velocity is getting larger. This guy is getting larger. So that tends to increase the EMF as it's falling faster. So you would think, based on that, the velocity gets more, right? You would think that that would cause the EMF to increase, right? But the Y, its distance from the wire also gets larger, you see? And then you have to square the distance. You see what happens? So it moves faster, but it moves into regions, it moves into more and more into regions of weaker magnetic field, you see? So then, how should I say this? It moves into regions of weaker magnetic field. So the rate of change of the 1 over the distance is less and less noticeable as the farther you get. Even though the V gets bigger, your distance from the wire is farther, and you're going into regions of weaker magnetic field. So the effect of the Faraday's law is less and less noticeable as you move into regions of weaker field. I see. That's kind of what's happening.